Good morning. Welcome to our webinar on LFA laser flash analysis. Today we'll be looking into using the LFA technique for testing ceramic material. So the way I would suggest we do it is we will have a general overview of the technique itself, show the various components, what it takes to do such a measurements, and also and then look into data obtained with the laser flash technique. So again, welcome. Thank you very much. My name is Marc-Antoine Thermidis. I'm here at NETZSCH, and I will be giving my ideas and my information, leading them over to you. So I would say just to start in terms of LFA technique, our line of instruments splits into three categories or three different instruments. One, primarily it depends on the temperature range one wants to perform the measurements. The first instrument, what we call the LFA 467, goes from minus 100 degrees Celsius to 500 degrees. The other one goes to a little bit higher temperature, from room temperature to 1250 degrees, and the last one goes all the way to 2800 degrees Celsius, starting from negative 70 degrees Celsius, and that will be the one we will be primarily looking into as we show data that we obtain on such materials. But before we go into those details, I think it's interesting to quickly have an overview on how this technique works. It's fairly simple. What you see on the screen here is a specimen located into a testing chamber. So the idea here is to bring the specimen to a given temperature, a constant temperature. And as it is now, you see the specimen is located in that furnace, but two things will happen at some point. From the bottom side, the lower side of the sample, there will be imagine the cylindrical surface. No, the flat surface of the sample at the bottom. At some point, a short energy pulse will be deposited on that surface. So that will be the first things that will happen. As a result, heat will diffuse through the specimen, through the thickness of the specimen, and reach the opposite face, what we call the top face of the specimen. And it happens that one infrared detector is monitoring the temperature of that surface. So the one surface receives a heat pulse of energy, the opposite surface is being monitored by an infrared detector, and that infrared detector will be essentially registering the temperature change of that surface. That's essentially what it is. The actual testing testing time is fairly short, as you will see. So let's go into a little bit more explanation on how this occurs. What you see here is a furnace. On top, you might be able to see the infrared detector, and at the bottom, the module that will produce that heat of energy. That pulse of energy can be produced either by a regular xenon flash or a laser. In that case, in this particular instance, for this illustration, we are using a sample xenon flash, but we do have units that actually use xenon flash. So you see the signal on the graph. On the graph we show here, we can see the signal from that detector, from the infrared detector, looking on the opposite surface of the sample. We can see that the signal of the detector is flat. In other words, the specimen is at steady state conditions, no temperature variations, and you see the corresponding signal from it. On the other side, at that time, you see here, we do produce and discharge that very short energy pulse. That's what you see shown below. As a result of that, the heat will then travel, as mentioned, through the thickness of that specimen, reach the back surface. When it reaches the back surface, the temperature of the back surface starts to increase due to that heat wave reaching this boundary. More radiation will be then emitted towards the detector, and that's exactly what you see, the signal from the detector increasing. Start to increase, will increase some more until it reaches a maximum, and eventually it will decrease because heat will be dissipated also to the environment. So again, at the beginning, detector signal flat, then there occurs the heat pulse, the flash, the short energy pulse, then the detector signal increases, reaches a maximum, and then decrease. Now the whole thing is how to calculate thermal diffusivity based on this simple technique. So what you see on the graph now is a curve, and in red, we are just showing such a characteristic curve. In this instance, we do assume that the signal of the detector will remain constant even after reaching the maximum. It is what is referred to mathematically to an adiabatic case. In other words, we assume that there are no heat losses through the environment. It's just a simplification. Things do occur in a much more complicated way. You do have heat losses, but for the sake of illustration right now, we will simply be looking at an adiabatic case. And the goal here is to see how do we calculate thermal diffusivity. And that is really what is interesting in this technique, is that you can, based on that simple curve, quickly have a quick estimation of what the diffusivity is. And that's what the formula shows here. It shows how you calculate diffusivity, denoted here as A is equal to 0.1388 times the thickness of the specimen in square divided by the half time. What makes this technique so attractive is the fact that to actually have a good approximation, first, you simply note the maximum temperature increase. As you see, denoted here as delta T max is the maximum temperature increase, is the difference between the level of the signal at the maximum and the level of the signal before the pulse occurred. So that's what is happening. Now imagine that you would consider the half extent of that temperature increase, what we call half delta T max, and you would go to the curve and find the corresponding time. This time is referred to half time, T sub 1/2, and then you use that time to then calculate diffusivity as you see here. So that's the one thing. Primarily, the laser flash technique allows you to compute and to calculate or to measure diffusivity directly. One more extension of that technique is to actually be able to measure also specific heat. The maximum reached by the specimen is actually influenced by the thermal mass of the specimen. So the mass times the specific heat. So it is a function of that. The lower the thermal mass of the specimen, the higher the maximum, and inversely so. Now imagine that you would keep this pulse of energy, the amount of energy released onto the specimen, if you keep that constant, and you would do the test, perform the test on 2 specimens at a time, one being a reference, consider the reference of which the specific heat is known, and also the mass, and the other being your specimen. Then by comparing those maxima, you actually can deduct the thermal the specific heat capacity. So in a way, you will get diffusivity directly and specific heat capacity by comparison with a known specimen or a reference specimen. So by combining diffusivity, specific heat, and density, one can then calculate the thermal or measure the thermal conductivity if thermal conductivity is the parameter of interest. So it turns out that most of the time that's what people want to do. That's really what they want to get to. But in that instance, the question might be, why do we even go through that to get the thermal conductivity? Why not use a regular steady state, a Fourier law-based type of technique? The answer is simply that it is true you could have used such a method, but the difficulty is the steady state techniques require, first of all, a long testing time. You have to wait for steady state. It's not so easy. And also your specimen tend to be fairly bigger. So and sometimes you even have to insert thermocouple inside the specimen itself. So it's not so easy to use. Just the laser flash is more is easier in that regard, because all you need is a tiny sample. Can be from 8 millimeter diameter if it's a disc, to, I don't know, 25 millimeter diameter. Can be all the way down to 0.1 millimeter thick, all the way to 3-5 millimeter thick. It depends on what the material is. So typically the specimen dimensions are much smaller, and the testing time is fairly much smaller. So we will be looking at such examples coming up next. What I'm showing now is simply one of our high temperature furnaces. It is the LFA 467 high temperature. It is, now you see inside as the furnace is being heated, and the samples are actually located inside, and the detector will be looking down onto the specimen. But you see, when you start reaching 800 degrees C, 1000 degrees C, typically that's the kind of how it looks like if you were to move the detector away. But let's go and see. We simply, by now we have define or explain or introduce how this technique is used. What you see now is data that we acquired once we know what the technique is. It's good to have a feeling about how such a technique performs. If one consider a reference material, in that case it's Inconel 600, we simply wanted to have a statement for the accuracy of this technique itself. So you will see the diffusivity measurement data matches very well with known published data, then the specific heat data in blue, and finally the calculated conductivity, again based on the measured diffusivity and measured specific heat combined into the calculated conductivity. And again, you can see the comparison between the published book data compared to what we measured. So it is clear that when it comes to this technique, accuracy, it's not of an issue at all if it's done properly. Now we will go into I would say two almost figure of merits of the technique itself. If you are on the market for an LFA instruments, you basically would like to have a way of judging or asserting how certain instrument from different manufacturers, how do they perform. One criteria is what I call the acquisition rate on the electronic side, how fast the data from the detector will be acquired. That's one thing to look at, and also how short the energy pulses can be. It's not so obvious to do all the time, because very often the time of this energy discharge, if a laser is being used, for example, is more or less fixed. It's not so easy to vary this time at will. It happens to be that we can do that. We can move and adjust the time at will from 20 microseconds to many milliseconds. Yes, so we have a pretty good way of doing that. So you must be able, this instrument must be able to sample the detector signal fast. By the way, we not only measure or save the detector signal coming from the infrared detector, we also monitor the energy pulse itself. So we are pretty sure of knowing how the pulse of energy is being applied. It is assumed that it should be short, infinitely short, but indeed we know that physically there is a time of discharge from that pulse. So we do account for that. So number one. Number two, we can have short pulses. What you see here on the graph is a case where we are showing and documenting that no matter, regardless of the thickness of the specimen, the measured diffusivity is essentially the same as expected. Just because I have a thinner specimen doesn't mean that the diffusivity will be different. The diffusivity is an intrinsic property of the material, so it shouldn't matter what the thickness is. Diffusivity has nothing to do with the thickness. The time of diffusion from the front surface to the back surface depends on the thickness for sure, but the actual thermal diffusivity is not. So in that case, copper, we choose copper because it's so difficult to measure at at very thin thickness, small thicknesses. As you see, from 3 millimeter, anybody can do that. We get a certain value, in that case close to 115, 116 millimeters square per second. But the difficulty starts to be when the thickness of that specimen decreases and decreases and decreases, and more and more and more. By the time we go to 0.25 millimeter, it should be that whatever we measure at a thickness, a specimen thickness of 0.25 millimeter is the same as the 3 millimeter. And that's what we do. And the only way you are able to get such a performance is if your acquisition rate from on your electronic, as mentioned before, again, detector signal, and also the pulse signal itself. So when we are able to do that at a very high acquisition rate, yes, you will be able to measure the diffusivity regardless of the thickness of the sample. Or let's to be more precise, as the thick of the sample specimen become thinner and thinner and thinner, your diffusivity value will remain constant as expected. And secondly, we also can produce the pulse duration very, very short, in that case all the way down to 20 microseconds. Again, it's important as you go towards a thinner specimen. So these two criteria is important. So that's what we illustrate here again. In that case, it's a graphite specimen. What would have happened if our acquisition rate and also our pulse duration were not short? So we would have had the impression that as the thickness of the specimen decreases, that the diffusivity also decreases, and we know that is not true. But again, by having these two capabilities, again, fast acquisition rate and very short pulses, we are able to maintain the diffusivity as expected, meaning at the same value, regardless of the thickness. That's one thing. The second thing too is that I did mention above that not only do we produce very short pulses, we also monitor or measure the duration of that pulse. We actually measure the pulse as it reaches the specimen, as it's being discharged from either the laser or the xenon flash. We actually know what that discharge is, and we take that into account in the calculation. It's very important. The red dot here depicts the fact that no matter what the pulse duration is, that's what we have on the axis. That's the pulse of the duration. If we make the pulse shorter and shorter and shorter, that's where the difficulty will start. And we are showing here that because we account for that in our calculation, we always, for a given specimen, and regardless of the sample pulse duration, we are able to calculate the diffusivity, and the diffusivity is come out to be the same. It doesn't matter what the discharge time is. If we didn't, if that was not done, you would have what is referred here as the blue dots. You would have the impression that as the pulse duration increases, that the specimen tend to have a lower diffusivity, which we know it's not the case. So again, it's another way to judge performance by looking at whether the pulse duration is being taken into account in the calculation. Now, the instrument we'll be focusing here today is the LFA 427. That's what you see depicted here on this slide. It goes from negative 120 degrees Celsius all the way to 2800 degrees Celsius. Very, very, very high temperatures. Very important is to be able at such high temperatures, or for certain material you might be testing, to be able to reach very high vacuum. That's what we document here, down to 10 to minus 5 millibar that can be achieved with it. And as mentioned, you are able to test very small sample dimensions, or even bigger, depending on what you're trying to do. But one of the things also, one of the feature, or what makes the LFA technique so attractive too, is the fact that you're able to measure specimen in many different shapes, sizes, and also form, whether they are in fiber type or liquid state or powder, etc. So we always have we can offer a wide selection of sample holders to accommodate your actual specimen. And that's in our case coming up, we'll be looking more into ceramics, but again, even if you were not testing ceramics, you still can do a lot with that method. What you see here is a quick it's a quick schematic of the 427. You see around the yellow area, that's where the furnace is inside. You see the furnace inside and the specimen located inside. That specimen will be brought to the whichever temperature you program. Once the temperature is stable, then the flash will be produced. In that case, it would be a laser, as you see on the bottom right. That's a laser connected to the furnace via an optical fiber. And then the radiation from the output from the optical fiber will be directed onto the front surface of the specimen. On the other side of the specimen, on the top of the schematic, that's where you see the infrared detector with the optics related to it. So you see the sensing system noted here. Very important to know that in that case we use a laser. Why? The question is simply that the reason is simply that we will tend to reach very high temperatures, as I mentioned, in that case 2000 plus degrees Celsius, and at such temperatures it would be very pretty much impossible to remain close to the specimen. So we use a laser, go far, and we use the spatial and time the spatial coherency of the laser to actually reach the specimen at whatever diameter we want to. So that's the reason why we use the laser in that case. At such temperatures, it becomes a MOS essentially. So you have a quick schematic of our 427. We can quickly summarize why people tend to use the laser flash again. First, you can measure over a wide range of specimen, or meaning of materials, from low diffusive, low conductive to very high diffusive, high conductive, typically, let's say from a polymer all the way up to diamond, and even thin diamond, very important. That's one of the things. So with one instrument, you're able to test a wide range of materials. Temperature range, very broad. The sample preparation compared to many steady state techniques is fairly simple. Simply getting a sample of a given size, a disc, a small tiny disc, or a small tiny parallelepiped or cube, depending on what you can, but it's fairly small. The measurement time, once the temperature has been achieved, and when the steady state is, when the temperature is constant within the furnace, the actual testing time is very, very, very fast, literally a few milliseconds. Again, you're able to test materials in different shape, forms, and state. That's the powder, fibers, liquids. Again, very important again is that the specimen is not, or the sensor is not interacting too much with the specimen. In other words, the sensor is not touching the specimen. Is very important, and built into the software are all type of models that would accommodate the actual specimen you're trying to test. Whether the sample is multi-layered and you want to characterize an unknown layer, whether the specimen is anisotropic, in other words, the diffusivity that is in a classic way measured through the thickness of the specimen. So whenever you use, whenever the LFA technique is used in the classic way, you obtain the diffusivity across the thickness of the specimen. But if it happens that that specimen is not, or the material is not isotropic, then there's also a way to measure the radial component of the diffusivity, or in that case of the conductivity. So there are models built into that. But here for today, the most important is the penetration model. Penetration means that if your specimen happens to be partly porous, then the pulse of energy will not only be absorbed on the front surface of the specimen, it will also make the pulse, it's the energy, the pulse will make its way down into the crevices of those voids, of those porous voids, essentially. So the heat energy is being absorbed over a certain thickness, not only on the front surface. So there are models designed for that, geared towards that, and when it comes to ceramics, it's fairly crucial to be able to account for that. The last thing, these are all the grounds we are covering before looking at actual test data. One thing that is very, very common when it comes to ceramic is that they tend to be semi-transparent or even transparent to the wavelengths of the laser. If it's the case, then you notice that what is shown here with the blue detector signal, the raw detector signal, you do notice that at the time of the discharge of the pulse, the detector signal suddenly increases too. It's simply because, and then you will see it following that sudden jump, you see the expected excursion, temperature excursion or signal excursion, the excursion of the signal from the detector. That's what you see. But this small energy jump at the beginning is actually due to radiation or partial radiation within the specimen. So if this was not accounted for, you will tend to measure a diffusivity, in that case 0.974 millimeter square per second. And we will see that when the radiation component is accounted for, the actual diffusivity only due to conduction is much smaller or close to what is expected. And that's what we show here when we use the appropriate model. Again, the model accounting for radiation through the specimen, then we can get a diffusivity that is exact, essentially close to the expected value. In that case, we were using a glassy ceramic, of which we knew the thermal diffusivity at 900 degrees, and what we get here, 0.877, is exactly what is expected. So the takeaway is that as you test, in that case, transparent samples are being tested, there are appropriate models geared towards that, and that's very important when it comes to ceramics. Now, in terms of application data, we will be looking at various materials. First, we're looking at bricks, as you see here. Those bricks tend to have many components, they are not necessarily isotropic. They are particles of different sizes, different natures. It's a mixture of, in this case, the first one would be magnesium oxide and alumina. I'm sorry. In the second case, it would be a mixture of alumina, silica, and silicon carbide. So these are fairly non-homogeneous type of material, and we will be going into the sequence of testing them and show what we get. There are two things we'll have to be using in those cases. First of all, they are bricks, ceramics, so slightly porous. We have a model for that, and they will tend to be also semi-transparent. We have the appropriate model for that too. As you see here is the results obtained with three specimens of each type for each brick. The reason why we show the results obtained on three different specimens is because the specimens are non-homogeneous. So depending on where the samples are obtained or where they are chosen from that block, so the diffusivity or the components might be slightly different. So in that case, it's good to have a series of specimens and see how those results vary from sample to sample. The diffusivity data are depicted again in the first case. Diffusivity will decrease sharply and then reach a certain minimum and then increase again. Specific heat will tend to increase, but overall, by the time specific heat and diffusivity are combined, we do see that the thermal conductivity will increase in time. That was for the first type of brick. That would be for the second one. Again, the resulting conductivity tend to increase with the temperature. Very important. So simply to give you an idea of what can be obtained for such ceramic, or in that case bricks, refractory bricks. Next, we'll be looking at a case where the specimen would be porous. I would say significantly porous. In that case, we are actually using a very extreme case. We are using a very soft, very porous graphite felt used for high temperature insulation. As expected, you can see that the thermal conductivity, when, for example, if the test is done with a purging atmosphere, in that case argon, you see what the obtained conductivity will be as compared to what would be obtained when vacuum is being applied. In that case, we are really using a pretty deep vacuum, and you see the difference. Essentially, the matrix, the core material itself, is far less conductive as it would appear whenever the contribution of the purging gas, in that case argon, is taken into account. And that's essentially what we are documenting, meaning that we can discriminate between conduction due to the material only, and also conduction due to a mixture of the matrix, meaning the material, and the contributing gases. The gases filling the voids, in that case, of that graphite felt, giving us confidence that even for such a sample that is far less porous, meaning the bricks I referred to before, we are still able to do it properly, to measure it properly. In the last case, we are looking, in this case right now, we're looking at a very porous type of ceramic that would be your material of interest in that case. Simply to say that because we can apply the penetration model, it is fairly expected that our values will be the measured diffusivity and or measured conductivity will be accurate, simply because we are using the appropriate model for that regard. Very important to insist on that, because that many times it is overlooked. You might be able to get away with it if the specimen is not, if the porosities are not too pronounced. But when it starts to be important, 5% up porosity, it's very critical to account for the beam penetration. Again, if I can summarize a little bit, is that the reason why we call that beam penetration is that because of the voids on the surface, the energy will not only be absorbed on the front surface, it will actually be absorbed through the voids at the bottoms of the voids too. Whatever void is exposed to the pulse of energy. Very important to account for that. Just to show you how the signal will look like if there were penetration or not, or how the model accounts for this penetration, for this porosity. On the left-hand side, that's what would happen. You will see that if you are using a standard model, at the beginning stage of the temperature excursion, the data feed will not be as expected. In other words, you do see a significant discrepancy between the data feed with the best possible standard model. Standard means model that do not account for penetration or for porosity. So you see how it will be. But if the proper model is used, in other words, if we use what is implemented in our software for porosity, if you use this model, then the data feed is much better. We account for the faster increase due to the porosity right at the beginning of the pulse, and overall the data feed is much better, and the calculated diffusivity is accordingly more accurate. That's something, and again, in that case, we are using an extreme case. We are using graphite felt, and even in that case, we are still able to measure diffusivity properly. It's very important, very critical. It's again one of the things I would suggest that you pay attention to if when judging the performance of any LFA instrumentation for the purpose of testing ceramics. Next, we'll be looking at some more application data. In that case, it will be silicon carbide. As you know, silicon carbide very critical in the industry, used in many instances: brakes, engines, high temperature insulation, high temperature components, whatever the application might be. It's a very interesting type of material. It will start, as you know, from a green body. Here, in that case, you're looking at silicon carbide diffusivity only being measured, let's say, from from room temperature all the way to 2000 plus degrees Celsius. You can see how we increase, how the temperature will increase, and how the diffusivity also will increase as we go with time. We will look closer in the next slide on how we start essentially from a green body. So that's what is depicted with the solid round dots, solid dots. So we start from room temperature, where we start from the green body. We increase the temperature slowly. Along the way, there will be some occurrences as the binders burning away and things like these. And at some point, the temperature of the sintering temperature will be achieved, and then the conductivity, the diffusivity will increase more and more, and will increase significantly. So essentially, we go from room temperature to 2000 plus degrees, and then keep measuring on the cooling side. So we went from room temperature to maximum temperature, and then we did all the measurement represented here with the dots. And then as we cool down back to room temperature, we keep measuring again. So that's what you see represented here with the squares. So you can see the big difference between the green body and the sintered and fired silicon carbide. That's the silicon carbide after firing, after sintering, after burning out, and you see the significant increase in terms of diffusivity. Again, that is expected. But in this measurement, we are able to document that to you. In one run, we measure going up and we measure going down, and you see the difference. Now, for a different type of ceramic, of silicon carbide, in that case, the green body has been a little bit modified with other components. If you remember the first slide and now the second slide, you see that above 2000 degrees, the behavior changes a little bit. And you because of probably additive added to that to the green body, or the grain size of the silicon carbide particles themselves. In any case, we see that by the time we cool down again, we're measuring going up and going down and cooling down, and you see that in this particular instance, compared to the previous slide, in the previous case, you see that the overall diffusivity and conductivity are much higher. And this is just to show you that what can be monitored or proven or observed with however you design your application. In that case, producing silicon carbide for higher conductivity and higher diffusivity. You see the results as presented here between first type of mixture of green body and a second type of mixture or green body. The next thing we'll be looking at is simply again for ceramics. The one thing we want to show here is that very often in that particular case, I did not account, or we did not show, the influence of sintering while increasing the temperature. And here what we'll be doing in that case, we will account for that, because the specimen is shrinking as expected, as desired, and as a result, the thickness of that specimen will change. It's very important to do that too. So we'll bring to bear also other instruments or other techniques. We will try to bring together measurement data obtained with a dilatometer, where we can measure the change in length. Within the LFA itself, you cannot measure how the thickness of the specimen is changing, but we can do that separately on a dilatometer and combine those data into the LFA measurement automatically and account for that. It's very interesting to be able to do that, because we know that indeed the specimen side, if I go back again to the previous thing, as the temperature is increasing, there are sintering occurring, so the thickness of the specimen will essentially decrease. So whatever you see here in terms of conductivity is actually an apparent conductivity, is not necessarily true, because we have to account for the change in thickness. And that's what we'll be doing here. Again, you see, we'll combine measurement obtained with a dilatometer with measurement obtained with a laser flash, with an LFA, the 427 in that case, and calculate the true diffusivity as a result of the sintering. So that's what you see on the on the graph here. Let's look first at the square, at the data represented here with a square, the red squares. That would be what would happen if we were just taking the green body and heating it up all the way to maximum temperature. So you will see at some point the sintering occurs suddenly. I mean, it occurs above 1,200 degrees Celsius, but you see the effect right here. And the reason why you see that effect here is because it is more pronounced than what I presented before. Is simply because the sintering is occurring and we accounting for it. Essentially, the specimen thickness is decreasing, sintering is occurring, more tighter bonds between the particles, and diffusivity is increasing significantly. And that's exactly what we are showing here with the red curve. Now, we are taking different cases where we would bring the specimen to a given temperature, remain fixed isothermal over a certain period of time, 4 hours, at an isotherm. Let's say in the first case, the star, the triangle curve dots, the triangle marks, we will keep the temperature at 1250 degrees we will go there, stay there, and then measure on the cooling side. And you see the diffusivity obtained. Obviously, this diffusivity is not as we would expect. In the next case, we do the initial isotherm as a slightly higher temperature, and we see that that would be the dots, and you see that as we keep measuring on the cooling side, the diffusivity increases much higher than what was obtained before at a 1250 degrees C isotherm. Now, if we do have this isotherm and we keep it long enough, in that case 4 hours at a much higher temperature, in that case 1400 degrees C, and then we keep measuring the diffusivity cooling down, we see that we obtain a much higher diffusivity. The purpose of this is to show you that the sintering is important. The temperature of sintering is very important. In a way, as what we would obtain heating up, if you go back to the square marks, what we would obtain with the square marks at the end after the sintering at above 1,400 degrees tend to be the same range as what would be obtained if we maintain an isotherm for 4 hours at 1,400 degrees C. Basically, the range of conductivity, diffusivity will be much higher. So, and then as we cool down again, we see that the diffusivity will increase, or will increase as the temperature is lower, essentially. But the point here is to say that it's a way for you to monitor or to see that the temperature at which the sintering will occur is also important. So you want to achieve, it's very important for subsequent process control to know at what temperature you should keep and for how long you should keep your specimen to make sure that sintering really occurs and that you obtain the highest possible diffusivity if this is your intention. So if you compared what we obtained with the diamond mark compared to what was obtained with the triangle mark, you can see how significantly higher the resulting diffusivity is. This is a statement for the temperature of sintering, temperature and time, how long you keep it at high elevated temperature and how high this temperature is. It's a very important criteria. This is expected for sure, but we are just documenting it. And most important here is that in that particular case, we are bringing the information obtained from a dilatometer, we are bringing them to bear too. So the measured or calculated diffusivity in this case is the correct diffusivity. In other words, we account for the thickness of the specimen. Very important for ceramics. In this part, in this instance now, we are showing the temperature profile that was obtained with a dilatometer, and we will be trying to match this temperature profile with our LFA too. So we program our LFA or the various temperature segments. We're programming in a way so as to mimic what was obtained or the way the dilatometer was used is also very important. So by the time we use these informations into the true calculation of the true diffusivity is actually correct. It's a very important point to do too. If when you're trying to match the information obtained with the dilatometer, it's very important to also be sure that you're following the same temperature profile. Again, this test documenting the influence of knowing the true thickness of the specimen in the ceramic material. You see heating up with a dilatometer, and then correcting. First of all, not accounting for the change in thickness, what you see in the dotted curve, and then what you would see with accounting for the change in thickness based on the data obtained from the dilatometer. So the first heating, you see it with and without correction, and you see that now if we were to perform a second heating, in other words, the sample has been fully sintered, cooled down, and then we heat it again, then you will obtain what you see here with the square marks. And at the end, at the maximum temperature, in that case 1600 degrees Celsius, you see that the diffusivity value obtained at that temperature is fairly equal to what was obtained with the corrected data during the first heating. So simply to say that if you did not account for the change in thickness, you might have had the impression that the diffusivity obtained at higher temperature is slightly lower than what was obtained if during the first heating the contribution of the shrinkage was not accounted for. Very important again to be knowledgeable about that. And if you will be making sintered application on sintering and things like these, it might be very advisable to make sure that you bear in mind that the thickness will change in some way you have to account for it. The good thing is that if you happen to have such informations, then you can input them or import them into our software, and the LFA software will account for that accordingly. The last thing I will be presenting is not necessarily related to ceramics, but yet to steel. In that case, it's a high temperature application steel. I'm just simply want to show you that why LFA technique is so attractive. It's simply that there are certain things you might be able to see, or certain effects you can see that you couldn't if you were using a steady state technique. In that case, we are showing that as you heat up steel, you go through the phase change around 700 some degrees, you see it, and when the sample melts at above 1400 degrees Celsius, you can see that too. So being able to monitor the thermal diffusivity as you go through those events is very interesting. If we were to look to combine all these informations with what would be obtained with a DSC, for example, then we can see whenever the phase change occurred, that what is represented here with the blue curve, we see the energetic events there. In the first peak of the DSC signal would be due to the phase change, and the second peak will be due to the melting of the specimen. So being able to monitor that through those events is really something that you probably would not be able to do so easily with a steady state method. Again, a statement for why people tend to use the LFA technique. And by the time diffusivity and specific heat and everything else is combined, you get the resulting conductivity. As you see here, one can still see the phase change around 700 degrees if conductivity was measured directly. It might not be so obvious to see really a phase change around 700 some degrees. By the time it is combined, obviously, whenever the sample melts, it's clearly seen above 1400 degrees Celsius. But again, this is a statement for why people tend to use the laser flash apparatus, the laser flash techniques for ceramics in our case, and even for other techniques, or for other type of materials, if this is of interest. At this point, that would conclude my presentation. If there are any questions, I would be happy to address them. So the one question I do see here, if you allow me to address that, the question reads: let's say you have 3 shots per temperature. This particular attendee want to know that if we take 3 different measurements at one temperature, let's say you have one specimen loaded into the apparatus, and you're trying to measure diffusivity, and you make 3 measurements at each temperature. He wants to know what value of diffusivity to take. First of all, if the specimen is not changing, if the specimen is stable at that temperature, the 3 values obtained for diffusivity should be fairly similar. If there are no change in the sample, it's not expected for the diffusivity to change. It is sometimes a way to statistically get good values or reproducible values. Number 1. Number 2, if those diffusivity change because the sample is shrinking or because the sample is unstable or something, and you actually get 3 values of diffusivity, the first approach would be to probably consider the average, but one can think that actually the first diffusivity, if the sample was not stable, the first value is probably important, as is also the last value at that fixed temperature, simply because it shows how the sample is changing over, even when you keep the temperature constant. So this is a particular type of application that I would like to, must be careful about. Again, it's very important. If the sample is not changing, if the sample is stable, there are no reason why the diffusivity should change. The tiny little heat or energy being introduced into the specimen will not change its thermophysical properties, will not change its diffusivity. And furthermore, the first measurement will be done at one time, and then there will be a certain lapse of time after which the second measurement is made. So by then the sample is back in steady state, so there are no reason why the diffusivity should change. So no problem regarding that at all. Hopefully I've been clear on that for that answer. So again, another question is, what is green body? What it means? The green body is in the ceramic world is referred as because it starts from particles, very fine ground particles that are mixed together with something, or with some I would say with some compounds, simply to keep it as let's say as a paste. So the green body means that the particles are mixed with other components, and it is expected as the temperature increases, those components will burn out. It's simply there to keep it geometrically or to keep it as a solid, but in fact it's not really a true ceramic, because the bond between the particles has not been established yet, and this is established when you go through sintering. So the state where at low temperature the fine powder-like particles are mixed with those compounds, this is called the green body. And typically they can shape the whatever however the final product should look like, will be put into a form, into a cast or something, or pressed into a given shape, and then heated up. And as it heats up, those components will burn out, and then the sintering will occur. The sintering is really where the bond between the tiny particles are created due to temperature. It's a sintering process. So the green body refers to the material at the beginning of the process. Another question is, how do we measure the signal from the detector, or do we actually measure the temperature? Two things very important is that we indeed do not measure the temperature, because, or we could if we calibrated the detector. It is important to know that in that case we don't really use a calibrated sensor. The detector is not necessarily calibrated. We can if we want to, but we don't. The reason why is because we always measure a signal relative to a prior state. So we have steady state, the detector signal is at a level, and then we introduce the short pulse, and that signal increase, etc. So this, we know there will be a temperature increase, and there will be a change in radiated energy from the surface, and a change in the detector signal accordingly. But the change in temperature is so small, far less than 10 degrees, that we can assume that the signal from the detector is proportional to the temperature range of the detector. the signal obtained from the detector is proportional to the temperature change of the surface. So proportionality is assured there, and that's not a problem. That's okay. It's mathematically sound to just use the signal from the detector instead of using just any temperature or measure the temperature directly. The actual temperature of the sample is measured through a thermocouple or through parametrically, but we can know the temperature of the sample before the test. Very important. Now the question is more related to what detector type is used for measurement down to -100 degrees Celsius. All we do is that we use different type of detectors for measurements. Let's say from room temperature to maximum 2,800 degrees Celsius. A regular indium antimonide detector is okay because the sensible range of radiation from 1 micron to 2 micron is 1 to 5 microns is okay, it's fine, because we know the useful radiation will be towards shorter wavelengths at high temperatures. Now when you go very deep in temperature, that case the useful radiation will occur at a much longer wavelength. In that case, we do use mercury cadmium telluride. It's a different type of infrared detector. The detector itself looks the same. It's the same thing. It's just the sensitive area is different. So for high temperature, for room temperature up, we use indium antimonide. From cryogenic temperatures -120, let's say, up to room temperature or even 500 degrees Celsius, we would use a different type of detector. It's called mercury cadmium telluride. So these two detectors can be used interchangeably, so no problem there at all. In pure, there's a question related to whether one can use pure hydrogen. Hydrogen. No, it's not. It's not certified for use. We know how dangerous it can be. But a mixture of hydrogen, 3 to 4%, 5% even, it's okay. Not a problem on that. But pure hydrogen, certainly not. It's not rated for such a dangerous application. But a mixture of low hydrogen content, we do that very often. No problem. Minimum thickness of the specimen, it will depend on the type of material. If it's a low conductive or low diffusive material, thickness can be very thin, as long as physically the specimen will be able to remain flat into the furnace, into the sample holder. There's no limitation there. As you go higher in temperature, as the diffusivity of the material increases, then at some point it will be too thin. You will have to refer to other techniques, very ultra fast pulse methods. Then as far as selecting the true or the most appropriate thickness, I would say that at some point you will get in touch with us and we'll make some recommendation what it will be. But definitely you're able to use it over a wide range of thicknesses. That's not the point. The problem is when it's too thin, at some point it becomes, imagine that you wanted to measure very thin diamond, for example. That would be, I'm talking micron and the micron level. That would be quite of a challenge for an LFA. There are other techniques for that. Now, if the sample becomes far too thin, but yet you still want to measure the diffusivity with the LFA, you can use the in-plane method. We do that very often for very thin material. We use the in-plane component. At least you can access the radial component of the diffusivity in that case. If it's an isotropic material, that's fine, no problem. Otherwise, there might be some limitation depending again on the diffusivity of the material. And again, we are able to make some recommendation if you contact us. So I think we are at the end of our presentation. Thank you very much for your attention and see you soon. Goodbye.